Enough of that. I want to now introduce Professor Murry Salby. He is a retired professor of sorts, if I can put it that way, originally from the University of Colorado. But if you look at his sort of curriculum vitae, it's amazing. He's come all the way from Australia via Germany, and he's going back to Paris and then back to Australia. And we've really appreciated him coming. As a little flyer says on your seat, in a sense, this is a very self-financing exercise. Jeremy Grantham has not coughed up the cheque I was asking for, nor have the oil companies. So, in a sense, all help gratefully received from that point of view. But much more important is what Murry has to say and to show us. This is new work. Those of you who saw his material that was sort of back end of a year or so back, this is building on that, and it's all been done under his own steam. He's not, again, been living on grants in order to do this. So I'd like to introduce Murry Salby, please.
Thanks for the kind introduction, Philip. Also for generously arranging this forum. Philip should not be left to shoulder that burden alone. I wanted to retire in Australia. I just didn't expect to so soon. If I am in retirement, let there be no doubt, it is forced retirement after being prohibited from teaching climate and then having my research files confiscated. One property, however, could not be confiscated. The research I will describe goes to the core issue of climate change. Why is atmospheric CO2 increasing? The IPCC's position is exclusive. Increasing CO2 results from anthropogenic emission entirely. The analysis about to unfold was inspired in significant part by the following observation. During the 1990s, the rate of fossil fuel emission increased almost linearly, growing each year by 0.08 gigatons of carbon per year. Were it retained in the atmosphere, that growth of emission would be equivalent to an annual increase in the growth of atmospheric CO2 of 0.04 parts per million by volume, ppmv per year. After 2002, fossil fuel emission also increased linearly, but 3 times faster. By the end of the period, fossil fuel emission was almost twice as great. During the same period, CO2 increased linearly, especially after 1995, when it increased at about 2 ppmv per year. After 2002, CO2 also increased linearly, but at exactly the same rate. The growth of fossil fuel emission increased by a factor of 300%. The growth of CO2 didn't blink. How could this be? Say it ain't so. If you step back from the stream of increasingly absurd claims and consider the big picture, the observed behavior should hardly come as a surprise. This is an estimate of the CO2 budget by the IPCC itself. It's the checkbook of CO2, the financial ledger that determines its balance in the atmosphere. The human source is of order 5 gigatons per year. The rest involves natural sources and sinks. They are larger by 2 orders of magnitude. Of total emission, natural emission accounts for over 95%. Net emission is the balance of these entries in the CO2 checkbook. For it to be dominated by the anthropogenic component, natural emission and absorption would have to remain perfectly in balance. Even a minor imbalance would overshadow human emission. Of those dominant contributions to the CO2 budget, our knowledge is limited. Observations of natural sources and sinks are scarce. Their collective impact, however, is unambiguous. In the atmosphere, CO2 is conserved. Once introduced from the Earth's surface, it's neither produced nor destroyed. It's only rearranged by the atmospheric circulation. The rate of increase of atmospheric CO2, its growth rate, must therefore equal its rate of net emission from the Earth's surface. Embodied in this equation is the budget of atmospheric CO2, which determines its abundance. Net emission is just the sum of emission by all sources minus the sum of removal or absorption by all sinks. Among the sources is human emission. Everything else is natural. By the IPCC's own estimate, the human contribution is small. The rest, from natural sources and sinks, represents more than 95% of what determines atmospheric CO2. Net emission is a resultant of all contributions. It must equal the instantaneous growth rate of CO2. That property is derivable from the observed record of CO2. In green is net global emission of CO2 from all sources and sinks. Does net emission resemble the human contribution? Not really. The observed evolution of net emission bears no resemblance to its contribution from fossil fuel emission. In fact, the 2 records are incoherent. Net global emission evolves independently of the human contribution. Okay, is the discrepancy from fossil fuel emission small? Not really. Observed changes of net emission are huge, as large as 100%, as they are absent in the contribution from fossil fuel emission. Those changes of net emission can follow only from what remains, changes of natural emission. If net emission does not resemble human emission, what does it resemble? A clue comes from the evolution of CO2 during the last 2 decades. The growth of fossil fuel emission increased sharply by 300%. The growth of CO2, which follows from all contributions, remained constant. During this period, one other property also remained constant. Since 1997, global temperature has varied little. Except for weak cooling, it remained constant. Unlike observations of CO2, observations of its emission are scarce. All we have are local field measurements. They are few and far between. Nevertheless, those local observations reveal that CO2 emission is sensitive to surface properties of land as well as ocean. In contrast, anthropogenic emission is independent of surface properties. The sensitivity of emission observed locally is confirmed in the evolution of global CO2. In blue is the component of net global emission that operates dependently with surface properties. It tracks the observed evolution of net emission. The blue curve represents changes of CO2 emission that are induced by changes of surface properties. Achieving a correlation of 0.93, the induced component accounts for nearly all of the history of net global emission. The surface properties on which national emission depends are diverse, but one carries the lion's share. Temperature, by itself, achieves a correlation to the observed record of 0.8. It drives the thermally induced contribution to CO2 emission. Thermally induced emission, that's the blue curve, can be used to determine how much of the observed evolution of CO2 results from natural emission. Integrating thermally induced emission backward, namely subtracting from current CO2 how much derived from thermally induced emission during the preceding year. That's the value in the blue curve. Then subtracting how much derived from it during the year preceding that year, the next value in the blue curve, and so forth, obtains the evolution of thermally induced CO2. The contribution to observed CO2 from natural emission. In blue is thermally induced CO2 during the satellite era, when we have global observations of temperature. In green is observed CO2. The thermally induced component tracks the observed evolution. Both are plotted in CO2 mixing ratio, R, which measures its concentration in ppmv. Before 1980, there are no observations of global temperature needed to evaluate thermally induced CO2. Global temperature then must be estimated from the surface network of thermometers, which has limited coverage of the Earth. In black is thermally induced CO2 obtained from the surface network. The uncertainty, which derives from limited coverage, is shaded. As in the satellite era, the thermally induced component tracks observed CO2 over much of the 20th century. An interesting feature of working on this subject is the opportunity it affords to witness the metamorphosis of information as it's transferred from one party to the next. I've observed that with successive transfers, information evolves like summation of n to the nth power. It quickly loses any resemblance to its initial form. And if the transfer involves advocates, the information loss is instantaneous. This calculation integrates thermally induced emission backward from current CO2, which it equates to its thermally induced component then. That's clearly not the case. When I performed the calculation, I expected to find a discrepancy, which would then isolate the anthropogenic component of CO2. That's not what I found. With an observational precision, the evolution of observed CO2 and its thermally induced contribution are indistinguishable. Does this mean the anthropogenic contribution is zero? Of course not. It just means it's too small to be identified. That's not necessarily the end of the road. In science, an upper bound on an answer can be almost as powerful as the answer itself. Uncertainty in the thermally induced component limits its possible range. Thereby, it limits the possible range of anthropogenic CO2. That range is more transparent if, rather than integrating backward from current CO2, we integrate thermally induced emission forward from 19th century CO2. How much derived from thermally induced emission during 1 year, plus how much derived from thermally induced emission during the next year, and so forth. In the 19th century, anthropogenic emission was close to zero. CO2 then must reduce to the natural component, which is dominated by the thermally induced component of CO2. When integrated forward, the thermally induced component should eventually diverge from observed CO2. The discrepancy will then isolate the anthropogenic component. In black is thermally induced CO2 when integrated forward from 1880. Within observational precision, it too is indistinguishable from the observed evolution. Nevertheless, the natural component is bracketed by its range of uncertainty. Not all of that range is physically meaningful. The natural component cannot exceed overall CO2. It can't represent more CO2 than is present. The thermally induced component must therefore evolve somewhere in the restricted area of shading. Estimates of CO2 during the 19th century are of order 280 ppmv. I say of order because when one accounts for uncertainties that cloud proxies of atmospheric CO2, like ice cores, there's little evidence that CO2 was ever constant. Nevertheless, for those who accept proxy CO2 on face value, 280 ppmv is sacrosanct. The component of increased CO2 from thermally induced emission, RT, is then measured from that reference to the respective evolution in the shaded area. The discrepancy from observed CO2 then represents the anthropogenic component, RA. An upper bound is the maximum possible value of the anthropogenic component. It corresponds to the minimum possible value of the thermally induced component. That evolution lies at the lower edge of its possible range. Anthropogenic CO2 can then be compared against the overall increase of CO2. In 2007, its contribution to increased CO2 must be smaller than 33%. Can we deduce more about the role of anthropogenic CO2? Not from the dependence on temperature of CO2 emission. Further insight can come only from an alternate perspective. Remember the budget of atmospheric CO2. It governs the evolution of CO2. The growth rate of CO2 must equal its rate of net emission from the Earth's surface. Net emission of CO2 is just its overall emission minus its overall absorption. Or symbolically, emission E minus absorption A. This is the conservation equation for atmospheric CO2. It governs the evolution of CO2. From it, we can evaluate the characteristic time for absorption of CO2. It's evaluated the same way we evaluate the atmospheric residence time for any chemical species. In the conservation equation, we omit the source term. CO2 present initially, then simply decays through absorption. How fast it decays is measured by the normalized absorption rate, alpha. The rate of decay, scaled by how much CO2 is present. It reduces to just the absorption rate, A, divided by CO2 abundance, R. R then decays exponentially at rate alpha. Alpha has dimensions of inverse time. 1 over alpha therefore characterizes the time for absorption. The E-folding time, how long for CO2 to decrease by a factor of E, namely to 37% of its initial abundance. It equals the residence time of atmospheric CO2. After introduced, how long CO2 remains in the atmosphere. To determine alpha, we need only the absorption rate A and CO2 abundance, R. Their values are estimated by the IPCC, at least what the IPCC thinks they are. R is 750 in gigatons of carbon. A is 150 in gigatons per year. The normalized absorption rate is thus 5 years to the -1, a residence time of 5 years. In truth, I haven't a lot of confidence in this estimate. R is well determined. A, on the other hand, is little more than a guesstimate. Except for isolated field measurements, absorption, which is highly variable, is not observed. There's another avenue through which to determine alpha. As we've seen, net CO2 emission depends strongly on temperature. This makes CO2 dependent on temperature. That dependence is measured by the cross-correlation with temperature, not of CO2 emission, but of CO2 itself. Plotted here is the cross-correlation between CO2 and temperature as a function of lag between those properties. It measures how large of a change in CO2 results from a change in temperature, along with the relative timing of those changes. Their cross-correlation is significant across a wide range of positive lag, where changes of CO2 follow changes of temperature. An increase of temperature is followed 10 months later by an increase of CO2. Hence, like emission, CO2 is strongly dependent on temperature. Its lag behind temperature leaves unambiguous which is the horse and which is the cart. The interdependence of CO2 and temperature is also determined by theoretical constraints. The conservation equation governs the evolution of CO2. It must therefore also govern its cross-correlation with temperature, which induces changes of CO2. The growth rate of CO2 must equal emission, which we've seen depends on temperature, minus absorption, which depends on CO2 abundance. The more CO2, the faster it's absorbed. Emission is thus a function of temperature. Absorption is a function of CO2 abundance, R. Approximating each by a first-order Taylor series reduces the conservation equation to linear dependence on temperature and CO2 abundance. The change in thermally induced emission is then proportional to the change in temperature. The change in absorption of CO2 is then proportional to the change in abundance of CO2. The factor gamma is just the sensitivity to temperature of CO2 emission. The correlation between emission and temperature seen earlier. The factor alpha is the normalized absorption rate, which is to be determined. It defines a family of CO2 evolutions, each one corresponding to a different absorption rate, alpha. In this system, changes of CO2 are forced by changes of temperature. It can be rearranged into a system that governs the cross-correlation between CO2 and temperature. What's observed in the top panel. Solving that system yields the cross-correlation that's required by the conservation equation. Comparison with the observed cross-correlation then determines alpha. For alpha equal to 5 years to the minus 1, a residence time of 5 years. This is the theoretical cross-correlation. There's a third way to determine alpha. Ideally, we'd like to perform a controlled experiment to measure absorption. Remove all sources and watch what happens. But this system we don't control. It controls us. If we can't remove the sources, then we must account for them. To do that, we must follow CO2 in the atmosphere. We need a tracer of atmospheric CO2, a property that goes where CO2 goes. It turns out there's an excellent tracer of CO2, CO2 itself. Not all of it, a small but uniquely identifiable subset of CO2. Atmospheric carbon has atomic number 6 and mass 12, but a minuscule fraction, smaller than 1%, has 2 additional neutrons, giving it atomic mass 14. As it makes only a trace contribution, carbon-14 can change without changing overall CO2. Yet with a half-life of 5,000 years, it too is conserved in the atmosphere. Therefore, C14 goes wherever CO2 goes. Its analysis reveals absorption of CO2. A similar analysis has been conducted by Gösta Pettersson in Sweden. You should take a look at it. C14 is produced naturally in the stratosphere, upper levels of the atmosphere, which are stable and devoid of weather. Cosmic radiation, comprised of energetic protons, strikes air molecules, which then release a variety of atomic particles. Among them are neutrons. The neutrons are absorbed by nitrogen atoms, each of which then expels a proton. This reduces its atomic number from 7 to 6, while retaining its atomic mass of 14. Voila! What was nitrogen is now carbon, isotopic carbon, with atomic mass 14. Along with other CO2 molecules, C14 is carried poleward and downward by the gradual overturning circulation of the stratosphere, the so-called Brewer-Dobson circulation. It gradually introduces C14-enriched air into the troposphere over the winter pole. There, C14 is entrained in the more dynamic circulation of the troposphere. It quickly mixes C14 horizontally and vertically to the Earth's surface, where it's measured. C14 is also produced by humans through nuclear fission, which releases neutrons. During the 1950s and 60s, nuclear bomb tests elevated C14. That auxiliary source was removed in 1963 by the Nuclear Test Ban Treaty. That event switched on the clock in an unwitting experiment. With the auxiliary source removed, C14 decayed through unbalanced absorption. Within 2 decades, the nuclear surplus of C14 was history. The decay is almost perfectly exponential, with an e-folding time shorter than a decade. Equal to the residence time, this determines alpha. Exponential decay means that absorption of CO2 is proportional to the abundance of CO2. That was our approximation earlier. It's noteworthy that during the 70s and 80s, another source of C14 emerged. C14 is also released by nuclear power plants, which expanded then. Contamination from that additional source would artificially lengthen the apparent absorption time. The actual absorption time could be only shorter. For reference, in mauve is the absorption of CO2 in the world of climate models, which relies upon the so-called burn model of CO2. Notice the time range. It's not 20 years, it's 200 years. Even then, almost 30% of the CO2 present initially remains in the model world. For comparison, here's the observed absorption in the real world. The correlation between observed C14 and exponential decay quantifies what's visually obvious. Their correlation is 0.996. This means the first order Taylor series for absorption, wherein CO2 absorption is proportional to CO2 abundance, isn't just an approximation, it's close to exact. That determines absorption unambiguously. As we also know, fossil fuel emission, conservation equation for anthropogenic CO2 is completely defined. Under relevant conditions, it can be solved, even without a supercomputer. The anthropogenic component of CO2, Ra, is governed by a conservation equation of the same form. It's forced by anthropogenic emission. With the record of anthropogenic emission and an initial concentration, the evolution of anthropogenic CO2 is then entirely determined. Consider now fossil fuel emission during the last 2 decades. It increased linearly during the 90s and likewise after 2002, but 3 times faster. Suppose that fossil fuel emission before 2002 was constant, equal to its maximum during that period. The resulting anthropogenic CO2 is then an upper bound on how much could actually be present. Because actual emission was smaller, actual anthropogenic CO2 must likewise be smaller. The budget of CO2 then simplifies. For constant emission, EA0, and initial concentration of 0 anthropogenic CO2, Ra, will increase. So must its absorption, alpha times Ra. Eventually, absorption just balances the constant emission, EA0. Net emission then vanishes. So too must the rate of change of CO2. Anthropogenic CO2 then becomes constant. Under these conditions, the budget reduces to a balance between the competing influences on anthropogenic CO2. How fast it's introduced by emission then equals how fast it's removed by absorption. The constant level of CO2 that satisfies this balance is just the quotient of those competing influences. It defines the equilibrium level of anthropogenic CO2, the level at which its emission is balanced by its absorption. The equilibrium level at any instant is proportional to anthropogenic emission then. If emission is removed, the equilibrium level becomes zero. After about a decade, anthropogenic CO2 will disappear. The equilibrium level has similar dependence on absorption. If absorption is weak, alpha small, the residence time, 1 over alpha, is long. CO2 then accumulates, making the equilibrium level high. If absorption is strong, alpha large, the residence time is short. CO2 is then removed almost as fast as it's introduced, leaving the equilibrium level low. With fossil fuel emission equal to its maximum in 2002, the equilibrium level of anthropogenic CO2 is just under 30 ppmv. After 2002, when emission increases, anthropogenic CO2 also increases. Absorption, which is proportional CO2, then likewise increases. Eventually, growth of absorption matches growth of emission. Thereafter, they differ by only a constant. Net emission, the difference between emission and absorption, then becomes constant. So too then is the growth of CO2. If net emission is constant, CO2 growth is constant. Anthropogenic CO2, which was invariant before 2002, then increases linearly, like anthropogenic emission. Anthropogenic CO2 then grows in parallel with, but behind, its instantaneous equilibrium level, the quotient of instantaneous emission, and absorption rate alpha, which drifts higher. This evolution illustrates an important property of anthropogenic CO2. It has limited memory. CO2 at any instant equals its equilibrium level a decade earlier. CO2 continually chases, but never catches, that drifting equilibrium level. For this reason, anthropogenic CO2 depends on emission only about a decade into the past. Emission from earlier times is inconsequential. Its influence has been erased by absorption. The same property couples anthropogenic CO2 to current emission. If growth of emission stops, growth of anthropogenic CO2 stops. If growth of emission increases by 300%, growth of anthropogenic CO2 likewise increases by 300%. We can now evaluate the anthropogenic component of CO2. In 2007, when we previously evaluated it via the thermally induced component, scaling RA by the overall CO2 increase yields 29.5%. This is not the anthropogenic contribution to increase CO2. It's an upper bound on that contribution. The actual contribution must lie somewhere in the shaded area. A similar analysis can be performed on the historical record of fossil fuel emission. It increases steadily, almost exponentially. That is no accident. In black is the record of human population. One is almost a perfect substitute for the other. Every human has essential needs: light, heat, food, and their transport. Directly or indirectly, all require energy. They are the inexorable needs of humans, much of whom reside in remote regions of the undeveloped world. The tight relationship between fossil fuel emission and human population tells us something about the capacity of government to control emission. Today, nearly $2 trillion of public resources has been diverted to so-called renewable energy. It hasn't made a dent in this relationship. If your objective is to reduce fossil fuel emission, then investing in windmills and solar panels is a waste of time. What you should invest in is contraception. Because human population grows exponentially, so does fossil fuel emission. Fossil fuel emission is well described by exponential growth, with an e-folding time of about half a century. Exponential growth doesn't represent the short-term bumps and wiggles, but it does a superb job of capturing the long-term increase, which derives from the long-term increase of human population. With this for anthropogenic emission, the conservation equation can again be solved, but now from initial conditions in the 19th century. Observations of atmospheric CO2, however, began only with the instrumental era, around 1960. Before then, we have only proxy evidence, which is clouded by uncertainty. For direct comparison with observed behavior, we consider increases of CO2 during the instrumental era. In green is the observed increase of CO2, where here, delta R represents its increase since 1960. In red is the increase of anthropogenic CO2. Of the 30 ppmv increase since the 19th century, what you saw previously, 20 ppmv arose since 1960. In 2007, the anthropogenic contribution to increase CO2 is 28%. What remains is the natural contribution. It must represent 72% of the increase. The natural component involves many contributions. They depend on surface properties, which regulate exchanges with CO2 reservoirs at the Earth's surface. Those influential properties are diverse, but one carries the lion's share. In black is the increase of thermally induced CO2, along with its uncertainty. What you saw earlier, but now relative to its value in 1960. Within observational precision, the natural component and the thermally induced component are indistinguishable. Much the same applies with respect to observed CO2, inclusive of all contributions. As before, uncertainty in the thermally induced component provides an upper bound on the anthropogenic contribution. The thermally induced component must be greater than 67%. Consequently, the anthropogenic component must be smaller than 33%. Implied by the temperature dependence of CO2 emission, this upper bound is independent of the preceding analysis, which followed from observed absorption and the record of fossil fuel emission. Together, the two analyses of anthropogenic CO2 reflect a double-blind test. One knows nothing of the other. And this brings us to the first of two fundamental questions. How would CO2 have evolved during this period, were fossil fuel emission absent? The gentleman in the center of this image is familiar. The one to his left is Robert McNamara, Secretary of Defense under Kennedy and then Johnson, an era when the term crisis meant something. October 1962, America's high-altitude spy plane, the U-2, was conducting surveillance of the Caribbean when it spotted the erection of launch sites for ballistic missiles on the island of Cuba, just 100 kilometers south of Key West. If completed, those sites could deliver a devastating attack, taking out the eastern half of the U.S. American intelligence advised that although the delivery systems were there, nuclear warheads had not yet reached Cuba. Once they did, strategic negotiation would be much more difficult. On that advice, Kennedy thought that he held the deciding card, that he controlled the situation. Kennedy called Khrushchev's bluff. He imposed a blockade of Cuba, which was poised to confront inbound Russian ships. The two nuclear arsenals were eyeball to eyeball. The UN Security Council held emergency sessions. After sleepless nights on both sides of the Atlantic, Khrushchev turned back his ships. The world breathed a sigh of relief. The perception then was that Khrushchev had blinked. History would eventually reveal otherwise. 30 years later, McNamara had occasion to meet Castro, face to face. Only then did he learn that when Kennedy had called Khrushchev's bluff on the belief that there were no nuclear warheads in Cuba, in fact, 162 nuclear warheads were already in Cuba. More than enough to destroy every population center in the U.S. McNamara then confronted Castro with his options. Mr. President, I have three questions. 1, did you know the nuclear warheads were in Cuba? 2, if so, would you have recommended they be used? And 3, had they been used, what would have happened? Castro responded as follows. Mr. Secretary, I knew the nuclear warheads were in Cuba. I would not have recommended they be used. I did recommend they be used. But Khrushchev wouldn't listen to me. What would have happened? Complete annihilation. McNamara could not believe his ears. I'm sorry, we need a different interpreter. Later, McNamara conceded that unknown to those in the White House, the world had been a hair's width from nuclear Armageddon. that would have added a new dimension to the term climate change. In retrospect, perception differed critically from reality. Castro was mad. Kennedy was misled by his own bureaucracy. Khrushchev held the deciding card. Had he turned Castro loose, the outcome would have been very different. America was failed by its bureaucratic intelligence. It was saved not by informed maneuvering of its government, but by Khrushchev's composure under circumstances that could only be regarded as unenviable. Back to CO2. Suppose hypothetically that Khrushchev had not remained composed, that he'd reacted and called Kennedy's bluff, and that the events spiraled out of control into the unthinkable. Fossil fuel emission would have then ceased because there would have been no industry, nor anyone to operate it. After about a decade, the anthropogenic component of CO2 would have disappeared. CO2 would then have reduced to the natural component, evolving along the blue curve, as if fossil fuel emission had never existed. Under those circumstances, CO2 in 2007 would not have increased to 380 ppmv. It would have increased to only 360 ppmv. Moreover, a decade later, it would have still increased to 380 ppmv. The moral of this story: human emission may answer to government. Natural emission doesn't. As we've seen, the growth of fossil fuel emission is tightly coupled to the growth of human population. Growth of emission has obeyed this relationship for at least 200 years. Unless $2 trillion is diverted to contraception, it'll probably continue. The exponential growth of fossil fuel emission leads to the second of two fundamental questions. When will the fossil fuel component of increased CO2 reach 50% of its overall increase? Why is this important? If under the most optimistic circumstances, namely, if fossil fuel emission is eliminated entirely, we can't eliminate even half of the increase. What's the point? In 2014, the anthropogenic contribution to increased CO2 is less than 30%. Derived from the historical record of emission, that's close to the 29.5%, which followed from representing emission accurately only about a decade into the past. The equivalence underscores the limited memory of anthropogenic CO2. From this value, anthropogenic CO2 increases with the exponential increase of emission, chasing an equilibrium level that drifts progressively higher. For reference, in mauve is anthropogenic CO2 in the model world. There, it already exceeds 50% of increased CO2. Under such conditions, a 300% increase in the growth of fossil fuel emission must be mirrored by an increase in the growth of CO2. In the decade after 2002, CO2 would have then increased almost 100% more than the observed increase, which was nearly identical to the observed increase in the decade before 2002. The same discrepancy prevails in subsequent years. In the model world, anthropogenic CO2 increases faster, 2.5 times faster. Consequently, it's not long before anthropogenic CO2 represents almost all of the CO2 increase. Under conditions observed in the real world, total CO2 must also increase through its anthropogenic component and its thermally induced component, which follows from prevailing temperature. In green is 0.5 times the increase of total CO2. Where these curves cross is when the anthropogenic component of increased CO2 equals 50% of its overall increase. That condition is met in 2092, 80 years into the future. A further insight follows from the limited memory of anthropogenic CO2. Towards eliminating half or more of this increase, emission today is irrelevant. When the anthropogenic component does reach 50%, it will depend on emission only during the preceding 1 to 2 decades, 60 to 70 years from now. So there you have it. If we take drastic action, namely, if we eliminate fossil fuel emission entirely, in 80 years, we could thereafter, and only thereafter, eliminate as much as half of the CO2 increase. Of course, achieving that objective may require exterminating the human race, but it's theoretically possible. Not so fast. Tabulated here is the worldwide distribution of fossil fuel reserves, along with their projected lifetimes. These values are in 2012, well into the current renaissance of extraction. The projected life of coal is about a century. For natural gas, only half as long. For oil, even shorter. Our calculation of CO2 presumed that fossil fuel emission would continue indefinitely. It can't. After half a century, all that will remain is coal. Fossil fuel emission must then fall. By how much? Here again is the record of overall fossil fuel emission. In gray, the contribution from coal. It represents less than 25% of overall emission. After half a century, our calculation of CO2 must account for a decrease of fossil fuel emission of at least 75%. Oh, let's be generous. Let's presume it decreases by only 50%. And because we seek an upper bound, let's presume further that somehow subsequent emission continues to grow at the original rate. During the first half century, anthropogenic CO2 increases as before. Then, when emission is halved, anthropogenic CO2 chases a sharply reduced equilibrium level. When emission is halved, the equilibrium level is halved. After a transient adjustment, about a decade, CO2 resumes the growth with which it evolved previously. Total CO2 must undergo a similar adjustment through its anthropogenic component. In green is 0.5 times the increase of total CO2. We are now in a position to answer the question: when will the anthropogenic component of increased CO2 reach 50% of its overall increase? Under prevailing conditions, never. Before it can, fossil fuel reserves will be exhausted. Even if fossil fuel emission was eliminated entirely, more than half of the increase would continue. When all fossil fuel reserves have been exhausted, CO2 will have reached 690 ppmv. Even then, fossil fuel emission contributes less than 40% of the increase. What will be its impact then? Insight comes from a feature of radiative transfer in the atmosphere. Of the maximum energy that can be absorbed by CO2 and then re-emitted downward to warm the Earth's surface, most has already been absorbed. The preponderance has been absorbed not by CO2, but by water vapor and cloud. After including 200 ppmv of CO2, all that remains for absorption by additional CO2 are scraps. This feature is nicely illustrated by the detailed calculation of Harding. In blue is infrared opacity of the atmosphere as a function of CO2. It measures the direct radiative influence of greenhouse absorbers. Without any CO2, the opacity is 75%. Adding 280 ppmv of CO2 increases the opacity by 6%. Further increase of CO2 has only limited influence because the opacity has plateaued. Increasing CO2 all the way to its current level, 400 ppmv, increases opacity further by 0.6 of 1%. Of that, less than a third is from anthropogenic CO2, less than 0.2 of 1%. Its radiative influence on surface temperature of the Earth follows from a calculation of radiative equilibrium, wherein heat is transferred only radiatively. It yields an increase of temperature of less than 0.2 of 1 degree. This temperature perturbation represents the direct radiative effect of fossil fuel emission. We shouldn't get too excited about it. Once introduced, it can be amplified or diminished by feedback mechanisms. The feedbacks possible are countless. One, however, is so dominant it's seldom even mentioned. Convective feedback involves vertical overturning of air. It's a ubiquitous feature which maintains atmospheric stability. Other feedbacks operate on timescales comparable to radiative heating. Weeks, months, even longer. By comparison, convective feedback is instantaneous. It operates on a timescale of only minutes to hours. In the horse race to establish a new equilibrium state, convective feedback leaves others in the dust. Its importance is illustrated by its influence on radiative equilibrium temperature. In red is temperature structure under radiative equilibrium. Surface temperature exceeds 350 Kelvin, some 80 degrees centigrade. Such temperature is never observed. It's prevented by convective feedback. Notice the radiative equilibrium temperature decreases with altitude sharply, approaching the so-called skin temperature at the radiative top of the atmosphere. Where temperature decreases faster than dashed lines, the atmosphere is convectively unstable. Effectively heavy air, overlies effectively light air. Nature invokes the most efficient mechanism to remove the instability. Convective overturning mixes air vertically, reducing the vertical gradient of temperature. Eventually, temperature has been driven parallel to dashed lines. The instability has then been neutralized. In blue is the resulting temperature structure. It characterizes radiative convective equilibrium, wherein heat is transferred radiatively and convectively, achieving a surface temperature of about 285 Kelvin. It's close to what's observed. Convective feedback has cooled the surface by more than 60 degrees. Greenhouse warming has thereby been halved. Because it operates much faster than radiative heating, convective feedback maintains temperature close to the blue curve. Consider now an incremental increase of CO2. In dashed red is the new radiative equilibrium temperature. When driven to radiative convective equilibrium, its greenhouse warming is likewise halved. If, under radiative equilibrium, surface temperature is incrementally warmer by delta T, radiative equilibrium, then under radiative convective equilibrium, it's incrementally warmer by only half as much. At 400 ppmv, the anthropogenic perturbation of radiative equilibrium temperature is less than 0.2 degrees. Under radiative convective equilibrium, that perturbation is reduced to less than 0.1 of 1 degree. This is the hand dealt to other feedbacks by convective feedback. It is all those feedbacks have to operate on. The conventional reference for increased CO2 is a doubling over 19th century CO2, 560 ppmv. Let's sidestep that and cut to the chase. What will be its impact when all fossil fuel that can be emitted has been? Sometime in the 22nd century, CO2 will then be 690 ppmv. This will increase atmospheric opacity by another 1%. Even then, less than 40% of that is introduced by fossil fuel emission. Under radiative equilibrium, this further increases surface temperature by less than 0.6 of a degree. Under radiative convective equilibrium, that's reduced to less than 0.3 of 1 degree. To place this perturbation in perspective, here again is the observed record of global temperature. The end of the 20th century is warmer than the beginning by 0.8 degrees. This difference, however, results from just 2 periods, 2 decades during the Depression era and 2 at the close of the century. Over the 20th century as a whole, temperature exhibits no systematic change. It therefore has no systematic relationship to CO2, which increased steadily. Much of the inspiration for claims of global warming derives from the second of these periods, the 80s and 90s, which exhibited consecutive years of warming. CO2 then exceeded 350 ppmv, significantly above 19th century CO2. The 1930s and 40s also exhibited consecutive years of warming, just as long and even faster. But CO2 then was less than 300 ppmv, scarcely above the sacred value of 280. So there's just one question you have to ask yourselves. If increased CO2 at 350 ppmv caused consecutive years of warming during the 80s and 90s, did it also cause consecutive years of even faster warming during the Depression era, when CO2 was scarcely elevated? If you reach the conclusion that yes, almost no increase of CO2 caused those consecutive years of even faster warming, then you are well positioned to then ask, during the preceding decades, did increased CO2 also cause consecutive years of cooling that was almost as great? It can be safely concluded that these changes of global temperature reflect the range of natural variability. It is against this range which the anthropogenic perturbation must be evaluated. To be charitable, that perturbation is small, without huge amplification, which would also operate on much larger natural changes. The anthropogenic perturbation isn't even detectable. This leaves global temperature to be controlled by just about everything but fossil fuel emission. Does this sound familiar? That is what has been observed. Even a 300% increase in the growth of fossil fuel emission resulted in no detectable increase in the growth of CO2. And to state the obvious, if fossil fuel emission is not detectable in CO2, it could hardly be detectable in properties influenced by CO2. Because further increases of CO2 can exert only limited influence, the circumstances that have prevailed to date will likely remain. In light of the observed behavior, I don't foresee a need to pursue this subject further. It's thus apropos to give credit where credit is due. I became interested in CO2 by accident, circumstances that have proven ironic. My interest was piqued when I was producing a new book on the atmosphere and climate. I was then confronted with a fundamental contradiction between what was being sold versus what the atmosphere was clearly doing. I undertook production of that book because it was all that I could do after being left without resources that had been pledged to rebuild my research program at my new employment in Australia. It was those circumstances which led to this analysis of CO2. I couldn't have done it without them.
Christopher.
Professor Salby, I think we all want to start by just saying thank you. You are one of a tiny band of immensely courageous, genuine scientists who have had their livelihood and their professional career stolen from them, not because their science was bad, but because it was socially inconvenient, politically uncongenial, and financially unprofitable to the governing class. Your bravery in persisting with your research over so many years after this was done to you is commendable. The clarity, depth and breadth of your presentation, which has grown since I last saw it only a year ago and grown exponentially, is breathtaking. And my question, therefore, is this: when are you going to publish in a journal that they cannot ignore?
Thank you for your gracious remarks. I'm not worthy of them, but thank you nonetheless. The immediate answer to your question is that this material will not be published until the material from which it derives is published. That won't be published until I have recovered my research files and been reinstated in the field.
My name's James Aratoon. I very much enjoyed your talk. There's a few things that interest me. One is that the current set of global models are being, or in danger of being, invalidated by the current pause if it continues for longer. So I wondered whether you just...
I'm sorry, could you please speak slowly? There's an echo in the room and I'm having difficulty hearing you. No, it's fine. Just if you'll speak slowly, I'll be able to hear it up here.
The current set of global models are potentially will be undermined in future if the pause continues. The current pause in the global temperature rise continues for more than, say, another 5-10 years. And the error bands of the current set of models won't be able to keep that in the in the bounds of their predictive ability. So the question is this pause something you could comment on as perhaps something which results from for example, a hypothesis would be the maximum temperature of the Earth being reached where the emission of energy equals the incoming energy, and so there's a clamping effect, so the natural variability is reduced, one hypothesis. Or it's just a pause when we get further ups, further downs. How do you see your work feeding into a further sort of predictive abilities for future years, if you like?
Okay, well, the completed question is to try to articulate the mechanisms behind the so-called pause, which is this section here, in the last 18 years or so. And then there was an allusion to some connection to the divergence from model simulations. I may have to come back and have you articulate that. In my view, the terminology that is widely used of this being a pause is a misnomer. It paints a picture that the last 2 decades, when temperature did not warm, were unusual. If you look at that record, it was not the period after 1997 that was unusual, it was the 80s and 90s that was unusual. Out of 16 decades in this record, there are only 2 periods, each 2 decades long, where you had consecutive years of warming. That means there are 12 decades where there was no systematic change in temperature. So, in light of the entire record, what has transpired since 1997 is more like the rest of the record than it is during the 80s and 90s. Now, the second part of your question is, so if you're asking me what's causing the so-called pause, I would say the return to normality. I think the more interesting question is what caused the warming during the 80s and 90s. In the 3rd and certainly by the 4th IPCC report, they had locked into this period of consecutive years of warming and were able to tune the models to match that period of warming because they knew temperature was increasing systematically over 2 decades, and they had a variable that was increasing systematically over 2 decades, CO2. Now, any two variables, any two trends can always be matched against one another, but the covariance, the interdependence of those in its statistical sense is 0 because you can always match one trend with another trend. It doesn't mean those two variables are really related. And so while during this period they tracked, what happened with the models is that the models continued to follow the variable to which they were tuned, CO2. But Mother Nature left in the third act, and she went and did her own thing, and it is now this period where you have had no warming, in fact, if anything, slight cooling, is almost as long as this period when you had warming. So how long is it going to go on before you concede that it was that period of 80s and 90s that was really peculiar? Not the only time it's happened, and it will happen again. It happened before, in the 30s and 40s. But it clearly does not happen on an ongoing sense. And by the way, that increase, so give me a second and I'll address what I think is your other question, but I have to change files. Shall I do that? All right. This is 24 models from the IPCC. And before we get into the conspicuous part of what you see here in the heavy line, I'd like to call your attention to the fact that of these 24 models, on timescales of years to decades, they are completely independent. You couldn't have come up with a more independent, incoherent set of evolutions if you tried, which means that whatever predicted value of one of these models comes up with, it has no relationship whatsoever to any of these other models. There's only one thing consistent between these models, and it is this centennial drift to higher temperature. Now, there are two breaks in that upward shift of temperature. There's one in the early 80s and there's one in the early 90s. Those were both volcanic eruptions, El Chichon and Pinatubo. They are in the model simulations, but don't be fooled. These are not predicted features. The models are told when the eruptions happened, and we spray aerosol into the stratosphere that stays there for a long, long time, like about 3 years. And that aerosol looks like haze, and it scatters or reflects back to space a certain fraction of the incoming solar energy, which means that energy doesn't reach the Earth's surface, which is shielded, so it's cooled. And so those two eruptions cooled global temperature for anywhere from 0.2 to 0.4 degrees. If you remove those two cooling perturbations, what you see is a steady uptick of temperature. 80s, then the 90s, and then afterwards no volcanic eruptions, and the simulations just continue upward. Well, so this is what we know. These curves are now the observed temperatures from the microwave sounding unit satellite family, and you see that they track more or less these variations that are seen in the mean of the ensemble, the black curve, until about 97, and as we all know, they have diverged thereafter with no indication of them coming back. Now, if you take the mean of those 24 models, here's what you get. And it predicts warming by the end of the 21st century of about 3 degrees. There's just one problem with this, and that is that this temperature is determined entirely by just one variable. If I can find the right one, I may have lost it. This one. CO2. Global temperature in these simulations is a function of just one variable, CO2. And we know CO2 has increased last century, and it's going to continue to increase for at least another century or two. In these simulations, since they are moving in lockstep with CO2, the global temperature has to increase. But as you saw in that other slide, if I can find it, global temperature in the real world hasn't behaved that way. It's diverged, which means that the exaggerated dependence on CO2 in these models is not give it predictive skill, not even on the centennial time scale. So I hope that sort of got it, the question you were getting at with the models.
You wouldn't be surprised to see another 20 years.
Well, if I were going to be objective about it, and I look at the actual temperature record, I've got 12 decades out of 16 where there was no warming. So the odds are, 12 out of 16, 75% that it's not going to be warming.
I was going to ask about the fact you approached the thing from two different points of view to get the anthropogenic component out. And what you've presented are both upper bounds for that. As you know, my approach by Henry's law would give a much lower figure, actually.
Lower than 25%.
Yes. If you take the residence time that you've used, and that's based on bomb work, it is one of something over 30 experiments using different techniques. The bounds for the residence time using those techniques are from 4 to 25 years, with 5 to 6 years being close to the average of all of them. My question really is, if you take the two methods you've used and you look at the sensitivity to all of the factors, what is the bound then, the upper bound and the lower bound?
Well, the values I showed you were for the longest residence time. If I chose the shorter ones that I showed you, if anything, it would be lower. So I presented 3 different ways to infer the absorption time. I actually explored it in 5 different ways, and the other 2 give even shorter values. So I'm not going to split hairs on that matter, but I will just call to your attention whether it's 1 year, which is what one of them comes up with, or 4 years, or 5 years, or 8 years, which is the longest I used, it ain't 200 years.
Thank you. As I understand it, anthropogenic global warming is essentially an invention of the Club of Rome as a means of systematically removing the individual liberties and free speech of ordinary people and aid the implementation of the United Nations Agenda 21 and their Wildlands project. This is never spoken of in the general press or anywhere like that. Is there any reason for that?
I'm sorry, was that a question?
Yes.
Well, let me cop out and say that I'm an atmospheric physicist, so, and to be truthful, I couldn't hear the last part of the question. Could you repeat the last part?
And essentially to virtually reduce people to little more than slaves.
I think to be fair, Mike, this is the physics tonight.
Well, I've got a loud enough voice, I won't need that. My scientific question relates to one of the many fascinating new points in your presentation, which is the negative convective feedback, which operates over hours and days rather than centuries and millennia. How did you quantify that? And did you also consider another short-acting feedback which is strongly negative, in fact 3 times as negative as the models thought it would be, which is the evaporative feedback to temperature change?
Well, the evaporative feedback is coupled to convection, right? You have a vertical transport of sensible heat, which is temperature, and you have vertical transport of water vapor, which ends up having heating. The convective feedback that I looked at has implicit in it evaporative cooling that you're talking about, because it's all done relative to saturated stability, not dry stability, so it has it built into it, which is it's a good point, because much of the heat transfer is in fact latent heat transfer, not sensible heat transfer. And in terms of the time scale and how this is done, it actually just evolves from the way it was treated back in the 60s by Suki Manabe and others when they were trying to do numerical simulations of climate. You know, in a climate integration, especially back then, where you had comparatively primitive computers, you have to take a time step. So you jump, and what they were finding was, well, they could resolve with these discrete time steps the long-term feedbacks like radiation and all these others. But the convective feedback was so fast it just couldn't be resolved. And so what they did was, in one time step, if the atmosphere went unstable because of radiation, it made this temperature slope too steep, they instantly restored it to neutral stability, which was that blue curve that described radiative convective equilibrium. And so in these integrations, and in most integrations, you're never far from radiative convective equilibrium. In numerical weather prediction models, you have a couple of time steps that can neutralize them. But nonetheless, because of the convective processes occur on time scales of minutes to hours, it happens very quickly, and you never get far from neutral stability. Well, you quantify it by comparing the radiative equilibrium temperature structure versus the radiative convective equilibrium temperature structure, which is showed. So one of these is the temperature structure in a radiative equilibrium. The other one is the temperature structure in radiative convective equilibrium. And to go from one to the other, you can see how far it is. And the cooling that you see there, the very large cooling, is not mysterious, because what happens is in convection, you essentially homogenize a certain property, something like potential temperature, right? And so that vertical overturning or mixing homogenizes properties between the top, essentially the tropopause, the skin temperature, and the bottom. And so the temperature, you have to essentially reduce it by about half at the top and half at the bottom. And so that's why you're getting that huge cooling at the bottom.
Thank you for a very excellent lecture. I could follow it because I have an academic background, but I'm certain that our politicians that actually rules us, they don't. So about 14 days ago, I sent a mail to all the Norwegian members of parliament, and I tried to translate this problem in different words. And they were going to introduce a climate bill of some sort.
I'm sorry, is this in the United Kingdom or in Norway?
In Norway,
in England.
Yeah. You were visiting us in Oslo also. I couldn't attend at that time, therefore I went to London.
Right.
Anyway, I said it's something that bothers me, because it is actually nature itself that balances the CO2 between the ocean and the atmosphere. So if you are worried about that man produce more CO2 than nature, then nature then balance that, because it keeps that about 1 to 50. And if you, by some strange means, are able to take some of the CO2 away from the atmosphere, the ocean will immediately fill that up to keep that balance. So in a way, what you are doing is to almost make a political decision that in order to produce safer winter driving, you'll now predict that water shouldn't freeze unless it's -5 degrees centigrade. I repeated that about a week ago, Conservative Party in Norway. It was an annual meeting, about 200 present. And in the breaks, I've never met so many people coming over to me and ask Knut, is this really true? And I said, yes, it's true. What are we doing? So I hope that you can repeat that in proper English to your politicians, and hopefully they start to discuss, are we fueled by CCIT or what? A little comment to Kennedy and the Cuban crisis. I had a meeting approximately at that time with some admirals in Pentagon, and they insisted, all of them, that Kennedy actually told them to break the barrier or retract from a barrier, and Pentagon ignored it. So it was almost a second big Pego base.
Thank you, Knut.
Thank you.
Max.
What's the basis for your confidence that the net emissions will remain positive over the century scale, which I think you mentioned a couple of times?
Mm-hmm. So on the extrapolation forward over the 21st century?
Yeah, the extrapolation point, yes.
Mm-hmm.
Well, yes, I think in your answer to Lord Monckton, you mentioned also that you expected the CO2 to keep rising. The CO2,
we have measurements, actual measurements of only half a century, but to the degree that the CO2 in the firn of the ice core, namely in the upper levels, which are still communicating well with the atmosphere, is also increasing. That I think we have some confidence that it's been increasing for a century, and I showed you that 70% roughly was due to changes of natural emission, basically, right? So that's tied to temperature. So long as the temperature stays in the neighborhood of where it is, we have an idea of the continued growth of dermally induced CO2. So that's the basis for it. If temperature were to come down substantially, I mean, not like anything you've seen in the record of the last century, it could stop increasing. I don't think that's very likely. The rate of increase may change, but it's going to continue to increase, I suspect, for most of the next century.
So it's based partly on the observed frequency distribution, or distribution of frequencies that we've seen in the past in CO2 fluctuations.
Well, there's no
and also the fact that the current temperature is set at a point where emissions exceed abstractions.
That's right, it's the latter.
We're often told that CO2 levels may be higher now than in the last 30 or so million years. Does anything that you've done suggest that we've actually missed periods which are higher than that in the past? It's just a recording artifact, and they have been substantively higher than today.
Yeah, the short answer is absolutely. The difficulty with the proxies, in particular the ice proxy for CO2, is that it is subject to dissipative mechanisms that have occurred and operated on that CO2 between the time that the CO2 appeared and laid down in snow, eventually was compressed into ice, and then was extracted. And there's a complex series of processes that have influenced that mixing ratio. I have at the time, I'm not going to bore you with the details of it, but the bottom line is that if you make even a passing representation of what those mechanisms are that agrees with the observed behavior of different species in the ice, you find that the changes that are present in the ice that we extract now can grossly underestimate the swings of CO2 that actually occurred when it was laid down.
The big message that Murray has, in my view, is that he's shown that the IPCC assumption that all of the increase in carbon dioxide in the last 200 years has been because of our industrialization is garbage. That's the really big message, because what you've shown is that it's largely natural. We can argue about the extent to which the anthropogenic component is there, but the really big message is it's not us that's been causing that increase in CO2, it's natural.
I agree with that statement. If I just put up a quick graphic, waiting on the Atom CPU to... Oh, you don't have an Atom. I don't think this is an i7, though. Here, let me get to it quickly. whether it's, I mean, what all of these analyses, they point to the same ballpark, 25, 30%, something like that. But even if you want to even be more conservative and say, well, okay, maybe it's as much as 50%, okay? It means that 50% is not under your control. And so you have to make then a value judgment. Okay, you know, we exterminate the human race or whatever and get the fossil fuel emissions to zero, but you're still going to have 50% left. You don't drive that bus.
I think we'll draw the formal meeting to a close now. I think I'd like to end with a very huge thank you again to Murry. Let's give a round of applause, please.
Reiterate thanks to Philip Foster for arranging this, and keep him in mind.